All right, today we're jumping right into a cosmic detective story. This is genuinely one of the biggest, most mind-bending mysteries in all of modern physics. It's a case that revolves around a single number in our universe, a number that seems so perfectly, so impossibly fine-tuned, that it basically challenges everything we think we know about reality. So, just to give you a sense of what we're talking about here, imagine trying to balance a pencil on its tippy-tippy point. Okay, now imagine that pencil is a trillion miles tall, and it has to stay perfectly balanced for the entire age of the universe. That's the kind of unnatural, frankly absurd precision we're dealing with. It's a cosmic coincidence so extreme that physicists are pretty sure it's not a coincidence at all. It's a clue to something much, much deeper.
So, here's our game plan for cracking this case. We're going to start by understanding what we mean by a fine-tuned universe. Then we'll identify our main suspect, the problem particle. We'll lay out the evidence, the theory versus the hard reality. Then comes the big reveal, the shocking scale of the mismatch. And finally, we'll explore the search for a missing piece of the puzzle, something called protective symmetry.
Okay, so our investigation really kicks off with this fundamental conflict. It's this major clash between how our best theories, our most elegant mathematics, say the universe should work, and what our most precise instruments are actually telling us. And look, this isn't just a small rounding error. We're talking about a profound disagreement at the very heart of reality itself. This whole conflict actually has a name, the hierarchy problem, and it's basically a massive tug-of-war between a particle's theoretical behavior, how our math predicts it should act, and its measured properties, the stuff we can actually see and verify in experiments. It's a battle between our expectations and the cold, hard evidence. Every good mystery has that one central character, right? The one person of interest that everything seems to revolve around. And in this story, we have a very, very famous one. Yup, the Higgs boson. You've heard of it. It's the particle discovered back in 2012 that's responsible for giving other fundamental particles their mass. But it's also the source of this whole gigantic conflict. It is our prime suspect in this cosmic puzzle. So here's where it gets critical. We have a major disagreement between two sides. On one side, we've got our prediction, which is based on the beautiful, intricate mathematics of quantum field theory. And on the other side, we have reality, the actual, undeniable data coming out of experiments like the Large Hadron Collider. And when it comes to the Higgs boson, these two stories, they just don't add up. Okay, let's open up the evidence file and really examine how this case is built. We're going to break down exactly where the theoretical model and the measurable reality just completely part ways. This table really lays it all out, doesn't it? On the one hand, our predictions come from these awesome theoretical models. They're our best guess, our modeled expectations. But on the other hand, reality is built on hard empirical data. It's the verified ground truth. And just look at that last row. When these two fail to line up, it's not just a simple math error. It's a giant flashing sign that our whole framework is missing something huge, that it requires what physicists call new physics. So here's the real heart of it. We're not comparing two slightly different experimental results. No. We're comparing what we actually measure to what our theory says is natural. It's like quantum theory is screaming that the Higgs mass should be incredibly, incredibly heavy, that it wants to be pulled up to some massive energy scale. But then we go and measure it, and it's shockingly lightweight. And that brings us to the climax of our whole investigation, the numbers themselves. And I gotta tell you, you might want to brace yourself, because the scale of this discrepancy is, well, it's almost impossible to wrap your head around. The calculation itself is pretty simple. Step 1, we start with the mass that was actually measured at the LHC. Step 2, we add in something called the quantum correction. That's basically the influence that all the other particles in the universe are supposed to have on the Higgs. And then step 3, we just compare those two scales. Simple enough, right? First up, reality. Experiments have clocked the Higgs boson's mass at about 125 giga-electron volts, or GeV. Now, to put that into perspective, a single proton has a mass of about 1 GeV. So on the subatomic scale, this is a pretty hefty number, but it's manageable. This is our ground truth. This is real. Now for the theory. Quantum mechanics tells us that the Higgs mass should naturally be pulled up towards the highest possible energy scale we know of, the Planck scale. This is like the universe's ultimate speed limit, where gravity gets just as strong as all the other forces. And that value? It's about 10 to the 19 GeV. That is a 10 with 19 zeros after it, an absolutely colossal number. So what happens when you compare the two? Well, you get a mismatch of 10 to the power of 34. That is a 1 followed by 34 zeros. The theoretical natural value is quadrillions of times larger than what we actually measure. I'm not exaggerating when I say this is, without a doubt, the single worst prediction in the entire history of physics.
For our theory to actually match reality, two absolutely enormous numbers would have to cancel each other out almost perfectly. A particle's bare mass and its quantum corrections would need to be opposite in sign and be identical to a precision of 34 decimal places. Physicists have a term for this, fine-tuning. And it just feels completely, totally unnatural, like winning the cosmic lottery a billion times in a row.
Which, of course, leads us to the final and most crucial question of all. If this is such a gigantic problem, why does it only seem to be affecting the Higgs boson? What makes it so unnaturally special? I mean, what about all the other particles in the standard model? Why isn't the electron's mass a problem? Or the photons? Do they have some kind of alibi, some get-out-of-jail-free card that protects them from all this quantum craziness? Well, the answer is yes, they do. Other particles are shielded by these beautiful things called protective symmetries. The electron, for instance, is protected by chiral symmetry. The photon is protected by gauge symmetry. You can think of these symmetries as being like a bodyguard, automatically canceling out those huge quantum corrections and keeping the particle's mass small and stable. But the Higgs, well, the Higgs is out there all alone. It has no known protection, no bodyguard.
And that right there is the absolute core of the hierarchy problem. This vulnerability, this complete lack of a protective symmetry, is the central clue in our whole investigation. It is the number one reason, the primary motivation for physicists to hunt for theories beyond our current understanding, wild ideas like supersymmetry or extra dimensions that could finally provide the missing alibi for the Higgs.
So, we end up right back where we started, with a question that is so simple but so incredibly profound. It was never about conflicting data. It's about a universe that appears to be built on an impossible coincidence. Why is the Higgs mass so unnaturally, so absurdly, so ridiculously small? Solving that mystery might just be the key to unlocking the next great chapter in our understanding of the entire cosmos.